All right, welcome back. We are on chapter 12. This is the first video of chapter 12, and this chapter is going to be looking at solutions. And we're going to look at some definitions involving that, some of the energies involving with solutions in this first video. So let's get going with that. Some of this might be a little review, but since we're dealing with solutions, okay, and usually we're going to be dealing with aqueous solutions, which means dissolved in water, we should just kind of review a little bit about water. We know that water is all around us. Up to 78% of your body's by mass is made up of water. A lot of that in your brains and your lungs. The earth itself is covered with water. Over 70% of the earth is covered by water. So water is an important thing for our bodies, for the earth in general. And we have learned stuff previously, okay, in past chapters about water and why we call it the universal solvent, okay? So there's a couple of things here we want to just kind of recap again from previous chapters. Water has one oxygen, two hydrogen atoms, okay, covalently bonded together. Now, the way it does it, though, even though there's just one oxygen and two hydrogens on the side, it is not linear, okay? There was some other lone pairs on the oxygen to give it a bent shape. That was an important thing because the polarity does not cancel out. There was the oxygen wants to steal the electrons more. It's more electronegative, okay? So we have some dipole, we have interactions here between the oxygen and the hydrogen, causing it to have a strong dipole. And then if you have water molecules and more water molecules, okay, lots of water molecules around, they will interact with each other, and we call this the intermolecular forces. And for water now, they can undergo hydrogen bonding. So water has London dispersion, it has dipole-dipole, and then also hydrogen bonds, which make it have fairly strong interactions between water molecules. We talked about how that gives it properties such as a very high melting and boiling point. All right, that's just a little background about water. Let's just talk a little bit about solutions and some definitions here. A solution is a homogeneous mixture, okay, that comes back to that term from chapter 1, of two or more substances. Now, usually you'll have a solvent that's present in the largest amount in a solute. You could have one solute, you could have many solutes. Those are the things that are present in a smaller amount. The whole thing together makes up the solution. All right, so if you have the example here, some sugar dissolved in water, water is present in the greatest amount, so that's a solvent. The sugar would be the solute, and the whole thing is the solution. Now, why is this a solution? Okay, well, because the solution, remember, is variable. The composition can be variable. You could add a little bit of sugar or a lot of sugar, okay, and have it more concentrated. This solution right here, okay, we have a solid in a liquid, okay, so those are ones that you have seen and we've been familiar with. We could also have different types of solutions. So you can have gas solutions, so a mixture of different gases. Example there is air. You could have liquid and a liquid, okay, so in lab we often will do a titration of acetic acid, and that is the main ingredient in vinegar, okay, so the acetic acid is the solute in water, and we call that solution vinegar. So you have liquid-liquid, and you could also have a solid-solid solution, okay, example there would be a metal alloy. We've talked about those as well. All right, so lots of different types of solutions. Let's look at some of the energies involved in when you make these solutions. All right, so a couple of things here. This is particularly looking at an ionic salt, okay, and what happens. So there's three steps that need to kind of happen, and they happen simultaneously, but we're going to talk about them a little bit separately here. All right, so number one, the solute, in order for this ionic salt to go into solution, so the solute has to separate. What does that mean? Well, the solute, that's the thing present in the smallest amount. In this case, this is the solid ionic compound. All right, and this needs to break apart. It's in that strong crystal lattice. All right, so here's the picture here. You can see a sodium chloride example. We have that nice lattice holding the cations and anions together, ionic bonding taking place. And these ions, even though they're very attracted to each other, have to break apart and come out of the crystal lattice here. So that's the solute separation step. Then the other step, okay, the second one here, is involving the solvent. Now, we just talked about water and the hydrogen bonding that goes on between water molecules. Now, in order for the solute to come into the solvent itself needs to make room for that. I find this picture just to be a really kind of a silly one, but it gets the point across. Here's these water molecules. They're all nice interacting together, and they need to spread out, okay? So you're kind of having to separate and break apart some of the hydrogen bondings to make room for the solute to come in. Both of these steps, okay, this first step right here and this step right here, when you are breaking apart like the ionic compound or breaking apart intermolecular forces, that requires energy. Now the third step is called solvation. And this now that we have separated the solute, we have separated the solvent, now the solvation step is when you now form new interactions between the ionic compound and water. If you remember from our intermolecular forces, when you have an ion, okay, either a cation or an anion, and now they're interacting with water, this is called an ion dipole force. So that's a type of intermolecular force. And you should be able to recognize how the sodium ion, okay, the Na+, is surrounded by the partial negative of the oxygen of water. And you could draw a bunch more of the water molecules surrounding it, and the oxygen part would be surrounding all of the cation. The anion, okay, since it's partially, or the anion is negative, it would be surrounded by all the partial positive hydrogens from the water molecule. All right, so that is kind of a picture of what things look like. Here is just one more view. And let's kind of work this through as well. So just molecular level, I want you to be able to think what is going on. Here is the overall picture. You have that solid, okay, on the left-hand side here. That's in brown, all nice and together. That's the solute. And then you have the solvent, the thing present in greater amount. What it means to go into solution means that now the solute is going to break up and kind of be surrounded now in a mixture, a homogeneous mixture with the solution. All right, let's look at how you go from the initial to the final in those three steps again that we were just talking about. So the first step is the solute itself has to break apart. So you're breaking apart the ionic bonds that are going on here. This is going to require energy. You can see that I have delta E. That delta stands for change in energy. And since this is requiring energy, the change in energy here is positive. Second step, okay, or the second process, again, they all kind of happen simultaneously. This is when the solvent itself, okay, needs to break apart and make more room. Okay, so you have to kind of probably break some of these hydrogen bonds that are interacting with the water molecules to make room for the solute to come in. Again, since you're breaking apart and separating out some of the intermolecular forces, this will also take energy, so the change in energy here is positive. So far we're putting energy into the system. Then you have the third step, okay? And this is now, we have the solute separate, the solvent kind of separated out. Now you can join them together and make new interactions. These are those ion dipole interactions. This is the process of solvation. And here we have the change in energy negative. That means this releases energy. All right, so we have a play now on things requiring energy and releasing energy. If, okay, this reaction will be spontaneous, all right, you are overall going to be releasing more energy than you took in. We want systems to then decrease in energy. So if it requires energy, it might not be spontaneous. So there's a play on the parts that take energy versus the step that actually gives off energy. So we can look at the energies there a second in a little bit more detail. All right, so here are three examples. And you can see the change in energy, okay, labeled, and for the different steps. And you can then add them up to see if the system overall requires energy or releases energy. For this first one, all right, the solute and the solvent change in energy, okay, these are the positive changes in energy, are not as big, okay, the solvation end part releases more. So overall, your change in energy will be negative. All right, so that means this will dissolve, and overall, this will give off energy. Reactions that give off energy in the form of heat we call exothermic. All right, so when you mix this up, energy will be released. Now, so far in the previous chapter, I think this was from chapter 9, if I can remember correctly, this is when we were talking about solubility rules. Okay, we looked at putting salts into a solution and if they were soluble or not, or mixing different solutions and seeing if a precipitate formed. Did you ever wonder why some salts went into solution and were soluble and some of them were not soluble? Well, it has to do with some of this change in energy, okay? If the ionic salt had very tight solute interaction, so it was a really strong ionic compound, it might not win out when it goes into solution. The hydrogen bonds breaking apart, now forming ion dipole bonds with the salt might not be enough for it overall to release energy. So here's two other examples that kind of look like they require energy. Okay, so here is the solute separation step that requires energy, the solvent separation step that requires energy, and here is the solvation step that releases energy. But you can see if you add them up, okay, you still had to put more energy into the system. The second one right here is the same as well, okay, requires energy for those two steps, but you only release a little bit of energy when the solvation occurs, when the interactions between the solute and the solvent occur. This one, you had to put in quite a lot of energy for this to go. These are both endothermic reactions. All right, and you'll notice that we said one will probably dissolve and one will not dissolve. Does anyone think of what the difference is? They both have a change in energy being positive. Now, one is not as big, right? This one's much smaller than this one. And there's another process involved as well, and that has to do with entropy. So we're going to look at that the next slide. If the change in energy required for the reaction is not that great, okay, so if it's really close to zero, just a little bit positive, the reaction could still happen, okay, because we might be increasing in entropy. We'll look at that. So there's a play between energy and entropy. All right, so summing this up, if the change in energy is less than zero, okay, so it's a negative value, the substance will dissolve. And that was our first example. And then if the change in energy is greater than zero, it will probably not dissolve. Now, if it's really close to zero, we will still be increasing in entropy when we mix solutions together. And so we could have a chance that it does still dissolve. All right, so here is a question. A given solute in water, the energy change in energy for the solute separation is positive 835 kilojoules. The change in energy for the solvent separation is 98 kilojoules, and the change in energy for the solvation step is negative. You can notice this one's negative, the other ones are positive. Will this dissolve? All right, so the total change in energy would just be adding up the three energy changes here. So we have positive 835 plus a positive 98 and plus a negative 805. Add those together, and I got a positive 128 kilojoules. And so I would say this is probably most likely will not dissolve. All right, so let's then look at what I'm talking about where it's kind of close to zero, and that is dealing with the change in entropy. All right, so here we go. I'm going to just write a little bit on this slide. Entropy, we sometimes give the symbol, or it is given the symbol S, and this is a measure of energy dispersion or energy randomization. So if you can take a system and now disperse the energy in more ways and make it more random or disperse in the system, you will be increasing in energy, okay? So here's the natural tendency. Systems want to decrease in energy and increase in entropy. Now, why is it an increase in entropy when you mix two solutions? All right, so now they are more random, okay, and they're more dispersed. So if you have two liquids, this is the bottom one, or even the top example here with a solid and a liquid, when you have them separate, they have less entropy than once they're mixed together. There's more ways for the energy to be dispersed, all right? There's more random arrangements, so they would be higher in energy. So the examples here, when you make the solutions, you now have increase in entropy. So the change in entropy, entropy, I'm gonna fix that. Change in entropy has gone up. So systems tend to move in a way that energy is decreased and entropy has gone up. So even though it might require a little bit of energy to get a solution to go to get a solid to go into solution, because it also will increase the entropy, okay, they can kind of cancel out and get those reactions to still go. You can probably take an entire class and chapter as you learn more about thermodynamics, and you'll talk about entropy more in higher up classes, but this is as much as we need to know for this class. All right, so moving up, here is a couple good questions. So this is some questions I want you to maybe stop, okay, and take a break, talk about in your class. And there are important things to kind of realize, all right? So if you want to melt sodium chloride, okay, so if you get some table salt, you want to melt it, you need to get really high amount of heat put into the system before it will melt. All right, that's 1,474 degrees Fahrenheit. But if you just want the sodium chloride to go into solution, you can do that at room temperature. Why is that such a difference? And it's important to understand what it means to melt and what phase changes are going on when it's going into solution. So talk about that. And then also another good question is, sodium chloride, easily soluble in water. But if you put it in hexane, it's not soluble, or not as soluble, so it's insoluble. What is the difference? Why is it soluble in water but not in hexane? Another good question for you to take some time, talk about with your class, and figure out your answer.